Thank you for the introduction. It's a great honor and privilege to speak at this symposium. So today, I would like to share my perspective on the role of AI in advancing 6G and give you some examples where we applied these techniques in relevant communications problems. So as an introduction, in the time frame of developing 5G, we have actually advanced a lot of technologies that will help us in 6G. I'll start with kind of wireless connectivity physical layer. I think deploying and using multiple antennas, large antenna arrays and millimeter wave, as well as massive MIMO, has become really a technology that we can now begin to use more and more and see how we can advance that. We have also conquered lots of spectrum. Before 5G, we were residing in sub-6. Now we have millimeter wave. We are moving to sub-terahertz. There is a lot more we can exploit. At the same time, cloud has been providing us more and more compute capacity, as well as machine learning and AI in other domains kind of helped us solve very complex problems that we couldn't solve today. So we're now really at the point in time where we can kind of put all these great technologies together in this next phase of 6G. So now let me kind of give you, I didn't want to start with the use cases because some of these use cases we actually thought about in 5G, and I don't think we really made them happen. But for 6G, this is really what I believe will be something that will happen. And those are my top three choices, if you like. AR, VR, we have heard a lot in the panel today. I also believe that the world of autonomy, connected cars, autonomous connected cars, robots, and drones will be something that we need to enable with our wireless networks and industry automation. Now, with respect to what is really required for us, it's not, as already has been talked about, it's not just more data rate, more capacity. It's really, in my view, latency, supporting mobility, and reliability. So with respect to coming back to the technologies, and I already highlighted some of them, it is kind of recognized among both industry and academia that artificial intelligence will really help us with a lot of wireless design problems. I also think that we need to continue using antenna arrays, making even larger antenna arrays, and that can help us both for communications and sensing. Energy efficiency is also important because our physical layer designs, we talked about being battery efficient or even battery free. Extremely high data rates and moving to high frequency and mid-band spectrum. So now there are these new technologies that we didn't have in 5G, and those are joint communications and sensing, reconfigurable intelligent surfaces, and also non-terrestrial network that will play a role. So that's kind of the ecosystem of 6G enabling technologies. And in my lab at UCLA, we have been trying to kind of, through our creativity and kind of understanding, how can we advance this towards 6G. So in this talk, actually, this is a big vision. I would like to highlight some of the work that we are doing at UCLA towards 6G. So I lead UCLA Cores Lab, and kind of our research spans three layers. First layer is more on the physical layer side. And there we're looking at 5G, 6G antenna array architectures and processing. There are kind of two lines of work. One is more trying to facilitate kind of lower complexity devices, maybe edge or user terminals, and use machine learning for critical techniques such as beam training and tracking. I'll talk more about that in this talk. We also have, on the other side of the spectrum, extremely wideband antenna arrays with through-time delay that are helping us advance new modalities for beam training, tracking, data communication. Unfortunately, I won't be able to talk about that today because the focus is on AI and machine learning. Now, moving to the layer of more kind of networking, we're pursuing several directions in advancing network intelligence via RF sensing. So some of the themes are, how do we do positioning, assisted by machine learning and AI, or through AI and machine learning? How can we do spatial prediction? as well as some of the techniques related to physical layer security, which is RF fingerprinting and detection of anomalies in the network. And the third layer, or like third thrust in our research, is spectrum sharing and coexistence. We have already heard the need that we have to think about sharing eventually. And some of the topics are related to understanding interference in time, frequency, and space in the bands shared with incumbents such as radars or satellites, as well as interference coordination and suppression. Okay, so this is kind of the top overview of our research. In this talk, as I said, I will focus only on projects that are using AI and machine learning. But before I start with these kind of project examples, oftentimes, when my students approach me, I want to do AI, machine learning, and topic, I ask this question: why? Okay, let's first think about whether this is the right tool. And decisions are kind of based on what is really inherent nature of the problem. So I kind of broke them down into 4 categories. First one is, okay, so maybe we don't have a good model, right? Maybe you don't have a good channel model or model of your device or something of that kind, or maybe it's too simplified. But you can gather a lot of data. Data is abundant, and you can apply it. So some examples that I'll talk about today are, can we do a spatial prediction, or maybe use it for positioning with enough training? The other thrust of algorithms are, okay, we know how to solve it maybe through very complex optimization problems or some signal processing. Then maybe you cannot do compute in real time. So can you actually accelerate some of your algorithms through machine learning? Maybe not completely replace them, but use machine learning tool to do that. So I'll give some examples in antenna array processing for beam training and tracking. But I believe you can also use them for massive MIMO, choosing the optimal precoder, doing channel decoding, and so forth. The third thrust is, well, we sometimes have these completely novel applications. Basically, we don't have any model. We don't have analytical way of going about it. One example is actually related to the physical layer security, which is RF fingerprinting, using raw IQ samples from your devices and trying to recognize them and authenticate them. And many of us in academia, and DARPA had a big program, we actually have shown that you can actually use machine learning as a very powerful tool to authenticate and identify devices or anomaly detection. And the fourth thrust is kind of cross-domain algorithms. What that means is we know that, let's say in computer vision, people have developed very powerful algorithms that work on images or videos. Now, as wireless engineers, we have RF signals. So how can we actually leverage these tools in our application? Lots of applications are in sensing, right? I'll show some examples on spectrum sensing as well as radar sensing, where we can really see how we can map our problem or use these techniques, okay? So those are kind of, in my view, 4 areas where you should actually go for AI ML tool as your solution. So now let me kind of proceed to more technical part of my talk, and this is how we have used AI and ML in some wireless applications. So I've chosen 4 of them. First one will be related to low latency beam management. The second will be related to that network layer intelligence, which is using oral measurements from base stations to do the positioning. Third one is how can we actually predict kind of ray tracing level channel prediction much faster using machine learning. And the fourth one is related to the spectrum sharing and sensing problem, detecting radars in 3 gigahertz spectrum, as well as satellites angle of arrival estimation. Okay, so let me start first with the first example. So I worked in millimeter wave, when 5G kind of began, we all got excited about using millimeter wave spectrum and lots of bandwidth. Okay, we can build these antenna arrays and we can do. So everyone agreed that this beam alignment is a big problem. And there were lots of kind of thinking how we can accelerate it. Because it's not really that we cannot get the gain. We can build larger antennas and get that path loss. The problem is the blockage as soon as you move, you have to realign. So ideally, we would like to get Gini beam pointing direction, and then we can keep our millimeter wave communication. So how can we achieve that? Well, I want to contrast what is the traditional. Traditional is kind of relying on a mobile side through some sort of a beam sweep, which you can accelerate with some smart heuristic algorithms. There is a second thrust where you can actually use compressive sensing, which kind of relies on the fact of sparsity of millimeter wave channels. And that would kind of shift you to the mode of using these pseudo-random beams. And what is the win? The number of measurements you need to take logarithmically scales with the antenna array. So as we want to put more and more antennas, either on base station terminals or any device, this can help us tremendously because of that logarithmic scaling. Now, the problem is these patterns that are kind of pseudo-random are creating problem if you have any array impairments. If you don't have very calibrated array, these compressive sensing algorithms do not work. So this is actually what we explored. Can we combine this compressive sensing idea, but then use machine learning as an algorithm that can basically inherently learn how to resolve these patterns and find the direction of arrival? So the algorithm that we have developed is called MMRapid, and it's basically machine learning assisted beam alignment. So as I said, the mobile is going to use these pseudo-random beams, red, blue, and many of them, and collect these basically receive single strand measurements from your PSS sequence. Now, from the algorithm point of view, if the mobiles are oriented in this way or this way, what will be a difference in the measurements is that based on several beams that you use, you will get so-called fingerprint. So in order to resolve what is the best beam pointing direction, you need to find basically which angle of arrival your fingerprint matches to. So it's effectively a classification problem. So how can we solve the classification problem? Well, neural networks are very good at that. So we are kind of on a mobile side, collecting the measurements using these pseudo-random beams and asking this neural network to tell us or predict what is the best beam to point to. Now, you might say, well, how do you train it? And that's the best part, that radio can train itself online because the mobile has this standard protocol where it can actually do the beam sweeping. So while it's beam sweeping, it can actually create labels for the best direction. And then once it trains the neural network, it can switch by using only the pseudo-random beams. So, and why is that important is because every device has its own array impairments. So you have to kind of use this machine learning training for each device, and it can do it on its own. We have also done optimization of these beams, kind of finding what are the best beams that you can use to accelerate that. This is done through dictionary learning, as well as how can devices kind of train faster through transfer learning. Now, what's nice about MMRapid is that also it can be extended to the tracking problem. And this is, sometimes you have to align from scratch, but in mobility scenarios, maybe you just have to update your beam. So in the standard protocol, we have these additional CSI-RS, but again, can we reduce them? Because they're really eating up time for our effective transmission. So we have developed this approach that uses MMRapid to build some history window in terms of what are the directions where the mobile can point at, and then use LSTMs to generate predictions up to P time slots in advance. So, and again, the MMRapid kind of trains both LSTM and gives you the best beam pointing direction. So we have used actual measurements, and actually what was most important is to have the real array to show that there is a benefit compared to the compressive sensing approaches. So we have used this Terragraph, which is from Facebook channel Sounder at millimeter wave, that actually has real array, phase antenna array with real impairments. And we have collected lots of measurements both in line of sight as well as in multipath channels. Actually, that neural network that I've shown you was kind of expanded over time to handle multipath. So we actually did lots of also indoor experiments. So the results have shown and confirmed that the idea of doing these compressive beams makes sense because the number of measurements that we should use to achieve the good beam alignment measured by beam forming gain loss is significantly improved compared to just a search. This was a 36 by 8 planar array, but actually there were 36 effectively antennas that were controlled. And we see that the number of measurements to achieve, and this is the green one is our neural network driven, is indeed needing only 5 measurements to achieve below 1 dB loss. Now, what I'm showing here as the other colors are what we call a vanilla kind of OMP style of compressive sensing, which indeed shows that these algorithms, once you throw in real array and real impairments, will fail. You have to take a lot more measurements to compete with neural network. And with respect to prediction, that LSTM approach, our question was, by how much can we actually reduce our time between the CSI, RS, and kind of predict in the future? So indeed, there is a history window and then the prediction window that we kind of varied to measure the required gain loss. And we see that within 4 or 5 rapid history, as well as prediction within, let's say, 4 or 5, you are within 1 dB gain loss. So indeed, both beam training and beam tracking with this kind of fusion of compressive kind of sensing and machine learning provided significant gains in improving. And we believe that this is, as we scale to higher frequencies, if we really want to keep millimeter wave as a mobile technology, this will be very beneficial. So now let me proceed with the kind of second thrust, which is kind of on a layer of network intelligence. And I'll talk about 2 examples. One is related to positioning, and another one related to spatial prediction. Unfortunately, I won't have time to talk about RF fingerprinting. So now we have these base station deployed with capabilities to measure the time of flight, the received signal strength, and now with arrays, we can also measure the angle of arrival. There is actually lots of measurements that we can fuse from multiple base stations to get a high accuracy localization. Now, the problem is if you are talking about deployments in cities and vehicular environments, it's a very complex task to fuse these measurements. So what we have kind of posed as a research question is how can we use neural networks, right, to help us? I mean, we can definitely train it, maybe in a simulation environment. This is actually using the Wireless Insight RAMCOM software, where we can actually generate the training data. But then we wanted to explore the dynamics. What if we're using only a subset of base stations and that constellation changes? What if the users are mobile? Or what if we deploy it in a completely different environment? So now, I believe that it can be solved by machine learning, but the big question is how big that network needs to be and how much data do we need to throw into that problem. So as a solution, we have been exploring these hyperparameter networks that have been actually recently explored in other domains that really help us with creating this scalable as well as a robust approach to training the neural networks. So the hyper networks kind of have 2 parts. There is effectively a network that is providing the estimates from the inputs being angle of arrival, time of flight, and received signal strength for a number of base stations. And there is a network actually that is kind of parameterized by another hyper network that is creating parameters or basically your weights for the neural network as a function of what you see as a measurement. So basically, there is a set of inputs, and in the second network, you also feed input what is the constellation of base stations that you're using. So that and obviously, there is kind of some overlap, but you might introduce more or less number of base stations. So we have compared this approach of hypernetworks with a single model, which was extensively trained on all base stations, right? You take all base stations and you provide the best kind of one neural network, not hyper, just a single neural network to do the positioning. And then you kind of split it into these two networks, and then you do a randomization of constellations, meaning that you don't use, you're not locked to using all base stations or the one that you specifically know. So we see that there is a significant improvement gain for the hyperparameters, as well as, this is a busy slide, robustness with respect to changing the number of constellations. With a single model, if you don't train enough, you immediately start kind of increasing your error as the new constellations arise. The second related problem, which is also very important in many wireless applications, is spatial channel prediction, or what we call radio environmental map. Basically, the problem is if I have a transmitter at a particular location and I have a map of the environment, would I be able to predict the received signal strength anywhere in this, let's say, city block or even indoor? And the goal is actually, we already have a technique for that, which is ray tracing. Now, what is the goal? The goal is to get accuracy as good as ray tracing, but much faster, right? And why is that important? If you're doing, let's say, coverage prediction or network planning, okay, you can maybe run ray tracing and wait. But for digital twin, for positioning, for path planning, for our robots, or spectrum sharing, you need to have this information much faster. So we have, this problem was actually kind of explored with many groups in academia. And there was, last year, there was actually a competition at ICASP, Big Signal Processing Conference, where there was actually competition who can design this neural network approach with best accuracy and fastest implementation. So we actually won a second place, but let me, and here are the kind of numbers that we got. You can get this on a GPU. This was our one GPU performance, 6 to 14 milliseconds based on different network architectures. So what are the inputs? The input is on a given map, you give transmitter location, you give a map of buildings and their heights, and you might give some sparse measurements, but actually that's not required. From that point on, we can do a line of sight calculation. Turns out that this was actually a little bit of pre-processing that tremendously helped the neural networks do the spatial prediction. So this is actually our proposed approach, where we create what are the points on the map that have a line of sight, and then we feed these 3 inputs to, or optionally 4, to the neural networks. There are 2 CNNs. They're basically using this UNet architecture. And we have explored the KL, or mean square error loss. And this is kind of our predicted RF map. The winner in terms of best performance was actually KL loss and also using the line of sight. The improvement from line of sight comes in the accuracy, but you pay the price of about 8 milliseconds to do that computation. So we believe that this tool is useful for, as I said, many applications. And again, there are even more room for improvement in terms of speeding it up and improving the accuracy. Okay, so now, I don't know how I'm doing in terms of time. I have time. The last topic that I would like to cover is spectrum sharing and coexistence. We have heard today from several speakers that if we want to get more of a spectrum below 6 gigahertz, or even below 15, we have to learn how to share it. So we have been exploring advanced interference estimation techniques, both in terms of angle of arrival as well as time frequency understanding, as well as interference coordination and suppression. So the spectrum that we are all thinking about is the FR3 spectrum that spans from 7 to 24 gigahertz. And hopefully, a lot of spectrum there will be allocated for 6G. But that spectrum comes with lots of incumbents. And those incumbents are actually very different from what we dealt in the past. Some of them are actually radars, and then satellites, radio astronomers, and then potentially there is jamming problems. So now this is kind of something that we were trying to avoid for a long time, right? We're trying to kind of say, sharing with DoD and satellites is difficult, let's stay away. But FCC actually kind of posed a challenge. There was this CBRS band that was already kind of authorized for use on a shared basis with the Navy radars. That's a prime 3 gigahertz spectrum. And that's from 3.55 to 3.65. And there is another spectrum right below it, 3.1 to 3.4, again shared with radars. So the question of how can we use the spectrum that radar is the incumbent is very important. Now, the main challenge turns out, how can we actually operate in that spectrum and then detect the radar so that we avoid the interference? And the current solution is actually very rigid in a sense that it relies on a database, but there is also room for improvement in ORAN to kind of make this detection more reliable. So we have worked on, again, this is where applying tools from machine learning and AI communities in computer vision actually can help us solve these challenging problems of detecting unknown radar waveforms, right? Possibly very weak. And also what the challenge is, they're kind of potentially overlap with LTE or 5G interference. So it's not just detecting the radar, but allowing 5G and LTE to operate. But the goal is, if the radar is present, we should avoid it. So the approach that we have developed, it's called RAD-YOLO-LET. It uses the tool from computer vision, which is this YOLO, you only look once, which actually is very good at object detection. So that one is kind of taking the spectrogram, IQ sample spectrograms, and using the YOLO to decide whether the radar is present or not. And then if it's present, then it's actually trying to understand parameters of both radar and interference as objects, like when do they appear, time, frequency. So those are kind of all parameters that we can learn purely to this machine learning approach. And in terms of performance of the detection, we have compared it with some kind of SVM-based approaches. These are 5 radar types in CBRS band, where we see that SNR needs to be pretty high in order to detect it. And you remember, we want to detect it in the presence of interference. Now, there is a prior work on deep radar, which somewhat improved the performance. And this is our RAD-YOLO-LET, which kind of achieved 100% for 4 radar types. And then there is one challenging one, which, again, we pushed the boundary to maybe 14, 16 dB compared to the state of the art. And in the presence of LTE interference, again, we are seeing numbers of detection which are in the order of 95%, which basically proved that YOLO with, I forgot to mention important part is the detection of radar was actually facilitated by wavelet transforms, because these weak radar transmissions or pulses, we cannot really match filter them, because we don't know what the real parameters are. So the wavelets turn out to be a very good match filter for these 3 different wavelet filters to help us pull out the weak radar impulses from the interference. Okay, last example is now moving to coexistence with satellites. There, we see the problem as if we can identify their presence as well as direction where they're coming from, we can potentially find a way to suppress the interference, or when we transmit, create nulls, for example, in their direction. So again, the problem is, can we do it very fast, right? This is, again, non-cooperative. We don't have any pilots. We're basically relying on energy detection in this band. But potentially the base stations are equipped with these large antenna arrays. And then how can they detect this angle of arrival with high accuracy very fast? So we have developed this solution that starts with a sparse measurement to the FFT of the kind of spatial spectrum, and then use 2 neural networks to predict how many interferers we have. So there is a CNN, which is a classical predictor. And then the other one is interpolator. So basically taking this low resolution image, this is again kind of a computer vision approach, and train it to find these angle of arrival directions for the interference. So there is an interpolator style CNN. And then if you want to get to the super resolution, you actually have to do a little bit of signal processing, which are these red blocks. So again, here in spectrum sensing, I think machine learning approaches have given us actually lots of new ideas and ways of getting from these massive IQ samples with lots of unknown signals or features, how we can do detection and estimation fast. So in conclusion, in academia, I mean, I have lots of students who want to work on AI and ML, and lots of projects we have done have shown tangible gains. Lots of other groups in the US have also demonstrated either in the lab or through high fidelity simulation. There are also lots of public data sets where we all kind of try to benchmark and find a way to use AI and ML. So that's exciting. Another part is that in order to really proceed, we cannot just rely on AI and ML kind of solving everything. I feel like combining the domain expertise with these approaches is essential. For example, these array impairments that I talked about, it's really a hardware problem. If you're just a signal processing person and don't talk to the people who are designing phased arrays, that would not be something that you would think of. Computing is also another one. We got questions. Okay, you put a neural network, you claim that you have a fast algorithm. Can you compute it? What's the latency of that implementation? How can we accelerate? Make it low power? Do we understand propagation? So I think for our students, keeping that domain expertise and training in traditional EE and CS with ML is essential. Also, deployment cost, overhead of training, and scalability are important. And that's something that I think we need to also quantify and understand when we are proposing these solutions. In my view, as an academic, I can definitely pick problems and kind of try to argue that they can be adopted. But in order to make an impact and for this to make it into products, I think standardization, if you understand, is important. So how can we integrate these techniques, maybe in an incremental way and safe way, into the protocol stack? And also something that I cannot do in academia, but I would like to see how can we do this verification and quantification of what are the real gains at scale. Thank you so much. This is all I had. I would be happy to take questions.